Hello there. So hopefully this will be a video series where I try to help you understand the topics for the new syllabus for Bhutanese students. So it's the new Cambridge Aligned Grade 11 Mathematics, and essentially the first topic is about exponential and logarithmic functions. So hopefully I can make a playlist of videos walking you through the different topics that you have, and we'll try to do as much as possible. So this is video number 1. We're going to be talking about exponential and logarithmic functions. But before we do so, let's start with functions. And we are not going to go very much in depth because I think in a later chapter we have a whole chapter just dedicated to functions. But I think it helps to have a general idea of what a function is. So a function, f, it will take in an input. So it's like a computer. It takes in an input and it gives you an output. So basically your input will be some value of x and your output will be f of x is equal to something, right? So let's take a look at this. Let me give you a very simple function, is x plus 1. Now, say if my input x is equal to 1, then my output is 1 plus 1 equal to 2. So this is my input. This is my function. My function takes my input, does something to it, and gives me an output. So this is how a function works. It takes an input, it does something with it, it gives me an output. So it's like a computer. Take in an input, give me an output. So that is what a function does. That is how it is okay to understand functions for now. So another thing about function, or another way to understand or look at functions, is that you have a set of inputs being mapped to outputs. So your function f takes an input. So 1 is taken and it's mapped to 2. If you have 2, it's going to get mapped to 3. Why? F of 2 is 2 plus 1 equal to 3. We're talking about the same function here, x plus 1. So if you have, say, 5, then it's going to get mapped to 6. So it takes in an input and it maps it to an output. So that is another way to understand a function. So now, once we have this idea of function, another important thing to remember about function is that when you see the graph of a function, it must pass the vertical line test. So basically, let's go back to the function that I just gave you. F of x is x plus 1. So if I draw the graph, it's going to be a straight line. It's going to pass through here. It's going to look something like this. With this being 0, 1, this is going to be 1, 2, and so on. And this is going to be negative 1, 0. But this is basically f of x, the graph of f of x and x. And this is y. So if you're graphing y is equal to f of x here. And basically what the vertical line test tells me is that at any x point, at any point along this x-axis where you see the graph of the function, if you drop a vertical line, then it must only cut the curve or intersect the curve once. So a vertical line must cut or intersect the graph of a function only once. So you draw a vertical line, it should only intersect once for something to qualify to be a function. So because this line passes this test, then we can say that it is a function. Now let me give you an example of something that is not a function. So let's say I have my x and y axes here. So this is y, this is x. And let me try to graph the equation x squared plus y squared equals to 1. Now we haven't done this yet, but this is a circle. We will look at it in later chapters. Pardon that my circle looks very bad. But this circle, now this is 1, 1 squared. So this is actually the radius. So we have 1 comma 0 minus 1 comma 0, 0 comma 1, 0 comma negative 1. So yes, so if I draw a vertical line at x is equal to 0, then it actually cuts my graph at 2 points. So therefore, this graph, this curve, this equation is not a function. Can I make it into a function? Yes. If I erase the bottom part, if I only consider the top half of my semicircle, then it actually starts passing the vertical line test. Now if I draw a vertical line, then it only cuts the graph once. So I can convert a circle into a function by only considering either the top semicircle or the bottom semicircle. But in general, the graph of this circle is not a function because it does not pass the vertical line test. And another way to phrase the vertical line test is that one input or an input cannot be mapped to more than one output. So if I give you a table, x and y, and if I say if x is 1, y is 1, if x is 2, y is 1, if x is 1 again, y is 3, then this is not a function anymore. Not a function. This is what we call a relation, I think. But this is not a function anymore because the number 1 is being linked to 1 and 3. So for one input, we have more than one output. This is not possible for something to qualify to be a function. And this is the same thing that we were looking at the vertical line test. One input, which is 0, is being mapped to two output, minus 1 here and plus 1 there. So that's why it cannot be a function. If you put x is 0, you have y squared is equal to 1, y is equal to plus or minus 1. So you have two outputs for one input, x. So that is why a circle is not a function. So you can look at it in a tabular form, you can look at it via the graph, but basically the idea of the vertical line test is that for every input, there must only be one output. An input cannot be mapped to more than one output for something to qualify to be a function. So now that we have discussed functions and the vertical line test, let's look at the exponential function. So the exponential function f of x is given by a to the power x. And one very important thing is that a is positive. So now let's look at the graph. Actually, let me draw it bigger on both sides. Okay, so this is y, this is x, and we're trying to draw the graph of a to the power x. And let me just give you the graph, is that it looks something like this. It does not touch the x-axis, so it looks something like this. Okay, so this is the graph of y is equal to a to the power x, or f of x is equal to a to the power x. If x is 0, this is 1, as long as a is not 0. But we already said a is positive, so it can't be 0. So if you just look at it, if x is 0, y is a to the power 0 is equal to 1. So that is why it intersects it has this y-intercept. It intersects the y-axis at 0, 1. Now, if you look at it, if you think about it, if I increase x, if I take greater and greater values of x, and I have one important distinction here, is that my a is greater than 1. My a has to be bigger than 1 for the graph to look like this. So now, if I take bigger and bigger x, if a is greater than 1, if I take bigger and bigger values of x, then the function, the output is going to be increasing. And let me just give you an example. Say if a is 2, 2 to the power 1 is 2, 2 to the power 2 is 4, 2 to the power 3 is going to be 8. So it increases. As your x increases, your output is going to increase. So as output increases, as x increases, your a of x increases. It gets bigger and bigger. And overall, it is an increasing function, right? Now, if I look at the negative values here, because it looks like it's approaching 0, right? So if I look at that is 1 over 2 to the power positive 1 is 1 over 2 to the power negative 2 is 1 over 2 to the power 2 is equal to 1 over 4. So basically, this is 0.5, this is 0.25. So the more negative my exponent, the smaller the value, the smaller the output. So this is why the graph looks like this. So if I take more and more negative x, then my y, or a of x, gets smaller and smaller. So as x tends to negative infinity, a of x tends to 0. And we can actually look at this, because a to the power negative infinity, also this is a bad way to look at it, but this is just for you to understand, because you can't have, x cannot be infinity. Infinity is more of a concept rather than a number here. So a to the power infinity, and this is a very, very big number. And if you divide 1 by something that is very, very big, then you are going to get closer and closer to 0. So we say that as x tends to negative infinity, a of x tends to 0. And we'll look at this in more detail when we get to the chapter about limits. However, I said this is only if a is greater than 1. So what happens when a is less than 1? And the graph actually flips. So your graph starts to look something like this. So this is still 0, 1. This is if a is less than 1 and greater than 0. And why is this the case? If a is less than 1, then it's a decimal. It's 0 point something. It's 0 0.9, 0.8, but it must be less than 1. Or another way to think about it is that it's a proper fraction, right? It's say a over, we can write it as c over d, where c is less than d. If c is less than d, then a is less than 1, right? And c is positive. Both numbers are positive. And c is less than d. If c is less than d, then a is less than 1. If c is d, then a is 1, right? So if it's d over d, then it's just 1. And if it's something bigger than d, if c is bigger than d, then it's going to be greater than 1. So now, why does the graph look this way? And the idea is that, say, if I increase x, if I take, then by laws of exponents, you know that this is d to the power x, right? This is how your laws work. And basically, this is going to be smaller than and this is going to be bigger because d is greater than c, right? And so the higher and higher values of x I take, overall it's going to be smaller and smaller because the denominator increases faster, or denominator gets much bigger compared to your numerator. So as x tends to positive infinity, a of x tends to 0 for a less than 1 greater than 0. And I hope you understand why this is happening, because you can write a as c over d, where c is smaller than d, and your denominator gets bigger much faster, or it's much bigger when you raise it to a certain higher number of x, or certain value of x, than your numerator. So basically, your output is going to be less than 1. It's going to be less than 1, as you can see here. It's less than 1. And the higher x you take, if you take higher and higher values of x, then it's going to collapse. It's going to get closer and closer to 0 because the denominator grows, gets bigger much quicker than the numerator gets bigger. And if you take x is negative, if you take negative values of x, then, well, and let's say a, where let's say b, where b is equal to negative x, right? We want to, or let's say, we want to see what happens if b is negative. And basically, if you have, say, a number like 0.5, and if you are raising it to negative 2, then, well, that's 1 over 0.5 to the power positive 2, right? is 1 over 0.25 is actually equal to 4. 0.5 to the power negative 1 is equal to just 2. 0.5 to the power 0 is equal to 1. So as you can see, if I have something that is less than 1 here, and if I raise it to more and more negative values, then my answer is increasing, my output is increasing. So here, that is why the output increases here. The more negative my x gets, the output increases if a is less than 1, which I've written here. So now that we have discussed everything there is about exponential functions, let's talk about logarithmic functions. And basically, when we talk about logarithmic functions, and this is a very specific case where we have the base 10. So if I give you log base 10x of a, then there is a very easy way to write this as an exponential. Is basically you take your base, this is called your base, right? 10. It can be anything. It can be any number like e, it can be any variable, say c, it can be some c. Your base is some constant c. So it doesn't necessarily have to be 10. It can be any constant c. And you can choose c, and it can be any real number. But if you have a base 10, and if you have an expression in this form, then you're going to take your base 10, you're going to raise it to a, and that is going to be equal to x. So you take your base, you raise it to this power, and that is going to give you x. So when we write something like this, log base 10 of x, what we are trying to answer is that what is the power? So this is asking me, what is the power or the exponent I must raise my 10, my base, to get x. So I must raise 10 to some number to get x, right? And if I'm raising 10 to some number to get x, then that number is going to be a in this case. So 10 to the power a is going to be equal to x. So this side asks me, what is the power I must raise 10 to get x? And this just gives me the power. It says that that power is a. So if I raise 10 to a, then I should be getting x. So that is the idea of a logarithm. And we'll see it with any number later. But the textbook starts with base 10. So we will start with base 10. So now that you understand sort of what a logarithm is, so let's try to draw the graph of a logarithmic function, because graphs will help us throughout this course. Graphs are very, very useful. So if this is my log base 10 x, my f of x is equal to log base 10 of x, and the graph looks something like this, and this is 1, 0. Now you might be thinking, wait, if I draw the graph of, say, 10 to the power x, 10 falls under the situation where a is greater than 1, as we previously discussed. So my graph is going to look something like this. It's going to 0, 1. This is going to be 10 to the power x. This is log base 10 to the power x, right? These are the two graphs I have. If you notice here, the coordinates between these 2 points have just flipped, 0, 1 and 1, 0. And actually, if you look at any point here, it is a reflection about the line y equal to x. So if you reflect this graph, if you reflect the whole graph over this line, then you get actually the above graph. And that is a property of inverse functions. So let me just, although we haven't properly discussed inverses yet of a function, but basically log base 10 and 10 to the power x are inverse functions. And inverse functions satisfy this property. F of f inverse of x should equal to x, and f inverse f of x should equal to x. And basically, that means that 10 to the power log base 10 of x should equal to x, and log 10 to the power x should also equal to x. And this you will find is true. And let's try to think of why this is true, why these are inverses. Here, I am asking the question, what power must I raise 10 to get 10 to the power x? And I must raise 10 to x. 10 must be raised to x to get 10 to the power x. So this makes sense. And this basically is, so let's say log 10 to the power x, this gives me a power. If I raise 10, just by looking at this small box part, this says that 10, if I raise it to this whole power, then I should be getting x. So let me just say log base 10 to the power x is equal to p. This tells me that 10 to the power p is equal to x. And on this side, we have log base 10 to the power x, 10 raised to the power log base 10 to the power, we have 10 raised to the power log base 10x, and we can actually rewrite this because we just call this p, right? So 10 to the power p, and we know from this definition, from what we have previously discussed, that this is going to be x. So you can see that they are inverse functions. They satisfy the properties of inverse functions. So, and this is true for actually any base. We will discuss that later on. So this is how the graph looks like. However, and I will be showing you in a later video, or actually, let me just show it to you here, is that if a is less than 1 but greater than 0, then your log graph looks something like this. So it's not going to look the same as in the case where a is greater than 1. Because your exponential function is different. So when you reflect it over the line y is equal to x, the graph is going to look different. So we will try to use this graph, and you can try to think for yourself why the graph looks like this. Again, the coordinates have just switched. 0, 1 became 1, 0. It's the same here because they are reflections about the line y is equal to x. And you can try to think why, because we've already discussed why the graph looks like this, but you can think for yourself and try to solidify your understanding. But now that we have discussed everything there is to in the first section of the textbook, I think this is about everything. Let's try to do some questions. So these are the type of questions that are in the textbook. I expect that in your final exam or your test, the questions will be slightly harder or much harder because these are very, very fundamental. But this is the way to start. So let's convert 10 to the power x into logarithmic form. And basically what you want to do is this is your base. You're going to say, keep the same base, 10, and x. And basically what this is telling us is that if I raise 10 to the x power, I get 58. So if I use our understanding of our log, then 10 to x, this power gives me this value, 58, right? So this comes from something that we have previously discussed. So this is how you convert. You keep your base. If you are given 10 to the x is equal to 58, then you write log, you keep your base, and then when I raise 10 to x, then I am getting 58. That is how you solve it. So now we are asked to solve 10 to the power x is equal to 58, giving your answer to 3 significant figures. So we're solving for x. So now I actually want to convert to logarithm because I don't know x by just looking at it. But once I convert it into the logarithm, as I have here, I know that log 10, this is equal to x. And this is something that you can punch into your calculator. So I am using my FX72, and please give me a few seconds as I try to find where I just put my calculator. So I have an FX72 here. So I have an FX82. So basically, if you just look at log, there is log over your data key, over your close to your C and AC. So basically, you just want to put log, and if it just says log on your fx82, then it's assumed that the base is 10. So log or lg, usually it's understood that the base is 10. And we have another function called ln. This is also a logarithmic function that the base is e, where e is Euler's number. But we will get to there. So you just want to punch log and 58. And log 58 is equal to 1.76. And it says to 3 significant figures, so we're just going to leave our answer to 1.76. So let me just, and if you check here, 1.76. So that is your answer. So, okay, let's go to work example 1.2. Convert this to exponential form. So you want to take your base, raise it to this power, and that is going to be x. And that is your exponential form. And if it says solve to 3 significant figures, then you just want to punch this in your calculator again. 3.5 gives me 3162.27766. But then I want it to 3 significant figures. So that's 3160. And we'll just stop there, because this 0 is insignificant. It's not counted as a significant figures. Your 316, that is significant. So now let's do more examples. Find the value of log 10,000. Well, I know that 10,000 is 10 to the power 4. And basically, this part is asking me, what number must I raise, what exponent must I raise 10 to get 10 to the power 4? Well, I must raise it to 4. And actually, a trick is that you can bring this 4 to the front. You can drop your exponents to the front and log 10 to 10. What if I raise 10 to what value do I get 10? So that is 1. So your answer just ends up being 4. So here, log base 10, and this is, I think, 10 to the power negative 4. 10 to the power negative 1 is 0.1, negative 2 is 0.01, negative 3 is 0.001. So this is 10 to the power negative 4. And this simplifies to just negative 4, right? Because what number must I raise 10 to get 10 to the power negative 4? I must raise it to 10 negative 4. It makes sense. So our answer is negative 4. Or again, like I said, you can actually bring the negative 4 to the front and solve log base 10, 10. And this is just 1. So negative 4 times 1 is just negative 4. This is an interesting one because we want to simplify this. We want to write it in the base 10. So I have a log base 10. 1000 is 10 to the power 3. 10 square root of 10 is 10 to the power half. And knowing the laws of exponents, if I am multiplying a to the power c times a to the power b, this is equal to a to the power b plus c. So I am going to add 3 plus half. And that is, if you simplify, that is 7 by 2. And this gives me 7 by 2. You can bring 7 to the front and say that log base 10, 10 is just 1. So 7 by 2 times 1 is 7 by 2. Or you can just think of it as what number must I raise 10 to get 10 to the power 7 by 2. And that is just 7 by 2. So let's just check our answers. So 3.5. 3.5 is 7 by 2. So now let's do some more questions. And we're approaching the end of the section. So we'll go over the questions very quickly. So it just says convert from exponential to logarithmic form. What you want to do, you want to keep your base. Your base is 10. And basically you're saying that if I raise 10 to this power 2, I'm getting 100. So that is how you want to solve it. So keep your base. You put this number. You're saying that if you're raising 10 to x, you're getting 200. You're saying that you take your log, right? Your base is the same. You're saying that if you raise your 10 to this fairly x, you get 0.05. Now solve each of these equations to 3 significant figures. So you just want to convert this into logarithmic form. So you're saying that log 1052 is equal to x, and you want to put this in your calculator. So let me just do the first one for you. So log 52 is equal to 1.72 to 3 significant figures. I think Please, if I made a mistake at any point, feel free to correct me. And again, you want to just convert everything into a log here. If you're stuck on how to solve these type of equations, you usually want to change it to logarithms. And we want the logarithm to be the base that we have here. So this time it's going to be base 10. So we have log base 10 to 50 is equal to x. And this part, you can just punch it in your calculator. So in your calculator, the scientific calculators that you are using, you don't have to specify the base because there are only two bases that's inbuilt. You have base 10 and base e. And if you just press on the normal log button, it's already understood by your calculator that you are using the base 10. So this is again going to be log base 10 0.48 equal to x. So if you solve this, I think you should be getting a negative value. So log 0.48 is, yes, so it's negative 0.32 something 318. So you want to solve it. Convert from logarithmic form to exponential form. So you want to take your base, raise it to the power, and you get 10,000. Take your base, raise it to your power, and you get this value, x. Take your base, raise it to your power, you get x. And again, once you understand these conversions, then this becomes very easy. You understand this very, very quickly. So now if I have to solve, if I have a log equation, how do I solve it? And to solve it actually is, if these things are equal, then I want to look at the base and I want to raise. I want to say if these are equal value, then when I raise 10 to these values, then they must be the same thing, right? So basically, I want to take my base and I want to keep that base and I want to raise my base to both sides. So I have 10 to the power log base 10 of x and 10 to the power 1.88. And here, we have previously looked into this. This is just going to be x because I've showed you before, right? I've showed you that if I say log base 10x is equal to p, then I know that 10 to the power p is equal to x. And I just said that this is p. And if I have 10 to the power p, then that is just x. So overall, everything simplifies to x is equal to 1.88. So if I take 10 and I raise it to 1.88, I get 75.85. So this is going to be, sorry about that. This is going to be 75.6 to three significant figures, and everything else is the same. X is going to be 10 to the power 2.76 because if I raise 10 to both sides, then I just have x. Again, 10 to the both sides, and x is equal to 10 to the power negative 1.4. And this is something that you can easily put into your calculator. Now, without using a calculator, find the value of. These are slightly more interesting questions. So I can immediately see that this is going to be 2 because 10 to the power 2 is 100. And this is going to be negative 4 because this is 10 to the power negative 4. And 10 to the power negative 4 is just going to give you this. Okay, if I'm, in my haste, if I make any mistake, please feel free to correct me in the comment section. But again, this is log base 10, and I have 10 to the power 1 times 10 to the power half. I'm going to add the exponents, and if I add the exponents, I get 3 by 2. So overall, your answer is just going to be 3 by 2 or 1.5. Again, if I have to solve this one, then that is log base 10. I have 10 squared because 100 is 10 squared times 10 to the power 1 over 3. And you must be familiar with why I'm converting it like this, because you have learned how to deal with exponents before. So surds and exponents, you must have dealt it with in grade 10 or grade 9. But if I have nth root of a, that means a to the power 1 over n. So 1 over 3, and I want to add. So when I simplify, I'm going to get 2 plus 1 over 3. So that's going to be 6 over 3 plus 1 over 3. That's 7 over 3 when you simplify the fractions. And overall, your answer is just 7 over 3. And this one is the same thing. Log, you have 10 squared. And I'm trying to write everything in terms of my base here. So 100 is 10 squared. And we have 10 to the power 3 by 2. That is how you can write 1000. This is because this is, you can express it as the square root of 10 cubed, and you can write this as 3 by 2. Because you're just multiplying 10 cubed by, and you know that the power rule allows us to multiply these two. So we have 10 to the power 3 by 2. So I can actually subtract my powers now, because the laws of exponents allow me to do that. So that is 4 by 2 minus 3 by 2. That is just 1 by 2. So the answer just comes out to be 1 by 2. So now the final question, this is a slightly more interesting question, is that given that P and Q are positive and that this expression equals to 9, find the greatest possible value of P. And this is where I want to go back to my graph of, let's say, log base 10 of P, or X. And basically this is P, this is going to be, let's just say Y, so this is going to be Y. So if I draw this graph, it looks like this. This is 1, 0, and this is what I told you the log function looks like. So if P increases, it becomes more and more positive, then I can see that my Y also increases. It gets bigger and bigger, although it is increasing at a decreasing rate, something that we will discuss when we get to differentiation in later chapters. But basically, if my P is increasing, then my output is also increasing. Although, I'm sorry, my poor drawing makes it look like it's decreasing. But it's still going to be increasing, something like this. So if P increases, log base 10 of P also increases. So if my highest value, if I want the highest value, the greatest possible value of P, then this is going to be as big as possible. Or this is going to be slash greatest, right? It makes sense that this first part should be the biggest. So if I want to minimize my impact from the second part, then I will take Q equal to 1. So why am I taking Q equal to 1? Because if I have 10 and 1, then I know that 10 to the power 0 is 1. So actually this thing is just 0, right? Log base 10 of 1 is 0. So my second part is going to collapse to 0. So if P is the biggest, as big as possible, then my first part, this collapses to 0 when I select Q equal to 1. And my first part is as big as possible, right? The biggest value of P is going to give me the biggest value of my first part, and I don't want the second part to contribute to the sum. I want entirely the first part to be 9. If my second part was not 0, and again, it's going to be positive, right? If it's not 0, then it has to be positive, and it's something like 1 or 2, then this part can only be something like 8 or 7, and P is not going to be as big. And we just got this idea from the fact that if log 10P decreases, then P decreases. If log 10P increases, then P is increasing. So that gives us the idea that we want to minimize the impact from this part. So we select Q to be 1, and this part collapses to 0. So effectively, we're just solving log base 10P squared is equal to 9. So log base 10P squared is going to be 9 by 4. And log base 10P is going to be plus or minus, if I take the square root of both sides, 3 by 2. However, I want my P to be positive, which it always is, because P is always greater than 0, right? So what is the greatest possible value? Well, I can say that it is 10 to the power 3 by 2 is equal to P. Well, yes, you also have 10 to the power negative 3 by 2, because when you take the square root, it can be both negative plus or minus 3 by 2, because when you square plus 3 by 2 or minus 3 by 2, you still get 9 over 4, but this is smaller, right? 10 to the power 3 by 2 is bigger than 10 to the power minus 3 by 2. So this positive 3 by 2 And p being 10 to the power 3 by 2 is going to be the maximum or the greatest possible value of p. And that is about it for the first topic, and we'll move on to more things that we have to discuss in this chapter. And yeah, thank you for watching, and if you have any feedback, please feel free to leave it in the comment section. And yes, this is about it.